So, what's a pulley? Well, a pulley is in a class of simple machines with levers and wheels and inclined planes. But pulley is really simple. It's just a wheel or something with a rope around it. And what a pulley will do is it'll use a rope or string to transmit the force. Like if I had this block, weight or gravity is going to be pulling down on it, so it's weight, and it's going to transmit that force through the string until the string is pulling up. The tension of the string is pulling up on the other block, and vice versa. So it changes the direction of a force, but not the magnitude. So the easiest way to look at pulley problems is using free body diagrams. So the free body diagram for the block on the left, you'd have the tension force of the string pulling up and the weight of the block pulling down, the weight and the tension. And then for the right block, same thing, you have the tension pulling up and the weight pulling down. And what's different about pulleys is your forces aren't always going to be in the same direction, or well, the signs aren't going to be the same. For example, these two blocks, because we can assume that they're going to be moving one way or accelerating one way. If we assume that the left block's going to move down, then the right block has to move up because they're attached to the same string. And if we assume that the left block is moving down and it's accelerating downwards, then we can define our weight on the left box as positive and the tension as negative, because our downward forces will be positive because it's accelerating downwards. And conversely, for our right box, we can say that our tension force upwards will be positive for that box, and the weight force downwards will be negative for that box because it's going to be moving upwards. And if we do it this way, that means that all of our boxes are going to have positive acceleration. So for the first example, we'll have a pulley system that's not in equilibrium. With a pulley with two boxes, and those are going to be 5 and 13 kilograms. So two masses are attached to a pulley as pictured. A Assume the pulley is massless and friction is negligible. And this is important, that the pulley is massless and the friction is negligible. That's what's called an ideal pulley, and it's what you'll be dealing with mostly. It simplifies a lot of things. So, what is the magnitude of the acceleration of the 13 kilogram block? And what is the tension in the string? So, the easiest way, like I said before, is to just draw the free body diagrams. So, for the block on the left, you have the tension force in the string pulling up and the weight force pulling down. And on the right, same thing, tension pulling up and the weight pulling down. So we know that the bigger block is probably going to be going downwards, because it's heavier. So for that block, we're going to make the weight positive and the tension negative, and then the opposite for the block on the left. And because it's accelerating, we know that the sum of forces is not zero. So let's write our equations for this. The tension minus the weight equals the mass times acceleration, and that comes from Newton's second law. The sum of the forces equals mass times acceleration. So the tension minus 15 times 10 equals 5 times 8. And 15 times 10 comes from mass times acceleration due to gravity. So tension minus 50 equals 5a. Tension equals 5a plus 50. W minus t equals ma. So 13 times 10, which is weight equals mass times acceleration. Minus t equals 13a. So 130 minus t equals 13a. And here you can see we have two t's, so we can plug that t into that other one. So 130 minus, in parentheses, 5a plus 50 equals 13a. And next I'm just going to distribute the negative. 130 minus 5a minus 50 equals 13a. 130 equals, or 130 minus 50 equals 13a plus 5a. So 80 equals 18a, and a equals 80 divided by 18. Alright, my calculator. So 80 divided by 18 is equal to 4.44. So that's one of our answers. Acceleration equals 4.44 meters per second squared. So now using our acceleration, we can plug it back into there to find our tension. So 130 minus t equals 13 times our acceleration, 4.44. So 130 minus 13 times 4.44 equals t. My calculator, 13 times 4.44 is 57.72. Store that. And 130 minus recall 1 equals, our tension is 72.28 newtons, of course. So for the second example, we'll do a pulley system that's in equilibrium. So we have a block on the table, a string, there's a pulley, the string goes around the corner of the table, and then we have another block hanging from the table. So this pulley system is going to be in equilibrium, which means that the sum of the forces on each of the objects in the system is going to be equal to 0. So two masses are attached to a pulley as pictured. The system is in equilibrium. Assume the pulley is massless and friction between the string, and the pulley is negligible. So what is the coefficient of friction between the block and the table? And what is the tension in the string? So we can draw the free body diagram for the left one. So for this one, you can have the tension in the string pulling it to the right, and then the friction pulling against the motion. And then of course it has weight and the normal force balancing the weight. As for the block on the right, it's going to have the weight and the tension on the string pulling it up, balancing the weight. And because it's in equilibrium, we know that the sum of the forces is equal to 0. So that means for this block, the weight equals the normal force, and the force of friction equals the tension. And from there, well, the best way to do it is to determine the tension in the string. For the second block, the weight is equal to the tension, and 9 times 10 equals the tension, and that comes from weight equals mass times acceleration due to gravity. The mass is 9, and we can just say 10 is acceleration due to gravity. The tension is equal to 90 newtons, and we can plug that in there. So the force of friction is going to be also equal to 90. So the force of friction we know is equal to the normal force times the coefficient of friction. And we can find the normal force because the normal force is equal to the weight. And the weight is 6 times 10 because the mass is 6 and weight equals mass times gravity. So normal force is equal to 60. So putting that all together, we can say plug our normal force in there and our force of friction in there. So 90 equals 60 times the coefficient of friction. So that means the coefficient of friction equals 90 divided by 60. So the coefficient of friction is equal to 1.5. So the question also asks, what's the tension in the string? And we already figured that out. The tension equals 90 newtons. So for our third example, I'm gonna have a harder one with inclined planes and friction and 2 pulleys and 3 masses. And forgive me if it looks a bit tilted. That's just how it ended up. So if I have an incline and a table and a mass, and let's say there's a pulley up here, and that mass is connected to the pulley, and then there's another mass on the inclined plane that's also connected to the pulley. But in the angle of the inclined plane is 30 degrees. But we also have another pulley, and we have another mass on the table that's also connected to that pulley. And the string from that mass on the table to the pulley is also at an angle of 20 degrees. So three masses are attached to two pulleys as shown. The 12 kilogram mass is accelerating at 3 meters per second downwards, and that would be the mass in the middle. The coefficient of kinetic friction between the 5 kilogram block and the table, so this is the mass on the right, is 0.820. What is the coefficient of kinetic friction between the 2 kilogram block and the incline? So that's the mass on the left. Assume both pulleys are massless and friction between the strings and the pulleys is negligible. So both pulleys are ideal. Something we should all be grateful for. So to start off, as always, let's do our free body diagrams, because this problem is much more challenging than the other two. So starting with the one on the left, the 2 kilogram block, our tension force is pulling up and to the right. The friction force will be going against that, it's against the motion. The normal force is coming out of the plane, perpendicular to the plane, and the weight force obviously just goes straight down. And if we do the free body diagram for the one in the middle, we have the weight force pulling down, and then we have the tension from both the strings coming up. And actually, let's label these. So the one on the left will be T1, and one on the right will be T2. So T1 and T2, and that would make this T1. So for the mass on the right, the 5 kilogram mass, you have the tension from the string coming up and to the left, and then the force of friction going straight to the right from the plane. And then of course you have the weight always and the normal force coming out of the plane. So next we should split the forces in our free body diagrams into their components. So for this one, it's on an inclined plane, so I think the best thing to kind of do is imagine as if you were rotating it like that way. So instead of being on an inclined surface, it's kind of more of on a flat surface. So if it was on a flat surface, rotated that way, the tension's coming straight out to the right, and the force of friction is straight out to the left. The normal force will come straight out of the top, but the weight would be different. The weight would be kind of going left and down. So we split it into its components, the weight in the y direction and the weight in the x direction. So it fits into our new free body diagram. And so if we label these, our tension is going to be the plus because it's going to be moving up the plane, and our friction and weight in dx is going to be minus. And if we do our free body diagram for the mass on the right, we split our tension into its components, so tension in the x and tension in the y. And tension in the x is going to be plus, and force of friction is minus, because that block's going to be moving to the left. And we can label these two. Our weight's going to be the plus, and the tensions going up are going to be negative. So if we write out our equation for that, it'd be weight minus T1 minus T2 equals mass times acceleration. And that comes from Newton's second law, sum of the forces equals mass times acceleration. And the weight is 13 times 10, which comes from weight equals mass times acceleration due to gravity, minus T1 minus T2 equals 12 times 3. And the 3 comes from the acceleration given in the problem and the mass given. So 120 minus T1 minus T2 equals 36. So now we can write our equations for the right block. So the tension T2, because it's T2 in the x minus the force of friction equals the mass times the acceleration. And so we can kind of draw our triangle to figure out how to represent T2 in the x. So if that's T2 and our angle is 20 degrees, then the bottom leg would be T2 in the x, and that leg would be T2 in the y. So because we want the leg adjacent to the angle and we have the hypotenuse, T2, we're going to use cosine. So T2 times the cosine of 20, and our force of friction is equal to the normal force times the coefficient of kinetic friction, and our mass is 5 times the acceleration, which is 3. So let's calculate that. 20 cosine is 0.94. So 0.94 T2 minus, and our normal force would be equal to our weight, but there's also the tension in the y direction to take into account. So our weight is equal to T2 in the y plus the normal force. So using that, we can say our normal force is equal to our weight minus T2 in the y. So we can sub that in. So weight minus T2 in the y is equal to our normal force. and it's our normal force times our coefficient of kinetic friction, which it's given in the problem. It's 0.82, and it's equal to 15, because 5 times 3 is 15. So 0.94 T2 minus our weight, which is 5 times 10, minus our T2 and the y, which we can see from our triangle is T2 times, we want the opposite, and we have the hypotenuse, so it's T2 times the sine of our angle, 20, times 0.82 is equal to 15. So 0.94 T2 minus 50. Let's calculate that. The sine of 20 is 0.342 minus 0.342 T2 times 0.820 equals 15. And you might not be able to see, but I distributed the 0.82 to the 50 and the minus 0.342 T2. 50 times 0.82 is 41. 0.342 times 0.82 is 0.28. So just copying over what we had before. 0.942 T2 minus 41 minus 0.28 T2 equals 15. So we can distribute this negative outside the parentheses. So 0.94 T2 minus 41 plus 0.280 T2 equals 15. I forgot the T2. So 0.94 plus 0.28 is 1.22. So 1.22 T2 and then 15 plus 41. I don't even need a calculator for that, really. Equals 56. So T2 equals 56 divided by 1.22. So T2 is equal to 45.9 newtons. So now we have T2. If you remember from our other sheet, we had an equation that had a T1 and a T2 in it. That one right there. So let's just copy that down. 120 minus T1 minus T2 equals 36. So now we can take our T2 we just found and plug it in to the T2 already there. Then we can solve for T1. So 120 minus T1 minus 45.9 equals 36. So 120 minus 45.9. So we have negative T2 plus 74.1. equals 36. 36 minus 74.1. So negative T1 equals negative 38.1. So T1 equals 38.1. So now we have T2 and T1. So if we go back to our free body diagram that we had drawn of the left box, we can write out our equations for that. So I'm just gonna copy it over onto this sheet with the normal force up and the weight in the x direction, and then our T2 to the right, and our force of friction to the left, and our weight in the y, or I'm sorry, our weight in the x to the left. So now writing our equations, T2 minus the force of friction minus the weight in the x direction equals mass times acceleration. So T1 T1, I've been saying T2. T1 minus force of friction, which is normal force times the coefficient of kinetic friction, minus the weight in the x direction. And of course, the weight in our x direction is the sine of our angle, which is 30, which comes from the problem it was given. Times our normal, times our weight, which is equal to our normal force. See, we were given the 30 and the mass of our block, which was 2. So the sine of 30 times 2 times 10 is equal to the weight in the x direction. That's equal to mass times acceleration, which is 2 times the 3 we were given for the acceleration. So T1 minus the sine of 30, or the normal force, which is the cosine of 30 times 2 times 10 times the coefficient of friction, minus sine of 30 times 2 times 10 is just equal to 10, and 2 times 3 is 6. So T1 minus, and all that junk with the cosine, is equal to 17.31 coefficient of kinetic friction minus 10 equals 6. So T1 minus 16 equals 17.32 times the coefficient of kinetic friction. And we have our T1, so we can sub it in. So 38.1 minus 16 is equal to 17.32 times the coefficient of kinetic friction. So 38.1 minus 16 is 22.1. That's equal to 17.32 times the coefficient of kinetic friction. So the coefficient of kinetic friction is equal to 22.1 divided by 17.32, which is 1.276. And my pen won't work. that's it. So this is a really hard problem that you have to have knowledge of inclined planes as well. But if you can get this one, you're good to go on pulleys.